Hello everyone, myself Praveen Kumar Dubey. I am from final year student in Civil Engineering Department in Lucknow University. Today I am going to present my seminar on topic Permeable Reactive Barrier Technology. So let's begin. To the next slide. On this slide here are table of contents which we are going to discuss. First one is introduction, then about PRB, then types of contaminants, types of reactive walls, types of reactive processes, types of materials, applications of PRB, benefits of PRB, challenges in PRB, case studies, and future of PRB, then conclusion. Moving to the next slide, introduction. The first question that comes to your mind, what is PRB? PRB is an in-situ treatment technology that passively captures and treats contaminated groundwater plumes. They are designed to be permeable so that groundwater can flow through them at a similar rate to the surrounding aquifer. PRBs mitigate the migration of contaminants in subsurface environment by promoting various chemical and physical reactions within the groundwater. They involve strategically placing a barrier perpendicular to the groundwater flow, forcing contaminated water to pass through a reactive medium. PRBs can treat a diverse range of contaminants including organic compounds, heavy metal, and other pollutants like insecticides, pesticides, nitrates, nitrites, etc. So moving to the next slide, what is PRB and its key components? Permeable reactive barrier is a groundwater remediation technology designed to treat contaminated groundwater as it flows through the subsurface. Here are some key components of the permeable reactive barriers are permeable media, which is a porous material by which groundwater can flow. Reactive materials. The permeable media is often mixed with reactive substances that can chemically interact with and neutralize contaminants. Then hydraulic control. The design of the barrier considers the hydraulic properties to control the flow of groundwater through the reactive media. And the fourth one is configuration. PRBs can be installed in various configurations like continuous wall, funnel and gate, pulse injection, etc. Moving to the next slide, here you can see the schematic of permeable reactive barrier where barriers have contaminants like heavy metals, light non-aqueous phase liquids which can be kerosene, diesel, petrol, benzene, etc. and then dense non-aqueous phase liquid which can be electric transformer oil, chlorobenzene, chloromethane, trichloroethane, etc. are flowing through the groundwater plumes in the aquifer, and then permeable reactive barrier is cleaning them through a wall. Moving to the next slide, types of contaminants. PRBs are designed to treat a variety of contaminants commonly found in groundwater. The specific reactive media used in the PRB is chosen based on the type of contaminants present at the site. Here are some examples of contaminants that PRB can effectively treat. Number one is heavy metals. In heavy metals like arsenic, chromium, lead, mercury and cadmium. And then chlorinated solvents like trichloroethane, perchloroethylene and dichloroethylene. Then nitrates and nitrites. And petroleum hydrocarbons including volatile organic compounds and semi-volatile organic compounds. And fifth one is perfluorinated compounds like perfluorinated compound including perfluorooctonic acid and perfluorooctane sulfonic acid. And number 6 is organic compounds, which is pesticides, herbicides and industrial chemicals, all can be treated by the permeable reactive barrier. Moving to the next slide, types of reactive walls. There are mainly two types of reactive walls by configuration. Number one is continuous wall. This is the most common type of wall where the reactive media is installed in a continuous trench or wall across the path of the plume. It's simple to install and effective for the wide plumes. And the second one is funnel and gate type wall. This type of wall uses trenchless or seat pile excavation to funnel the contaminated water through a smaller treatment zone filled with reactive media. It's suitable for narrower plumes or situations where directing groundwater flow is desired. Here you can see in the image of the configuration of continuous and funnel gate wall. Moving to the next slide, types of reactive processes. There are a variety of ways that permeable reactive membranes can be used in order to remediate the groundwater. Mainly there are two processes. First one is Immobilization. Immobilization of contaminants in permeable reactive barriers occurs through sorption or precipitation. Organic compounds tend to undergo sorption due to hydrophobic expulsion from the surrounding water, where a metal tends to sorb through electrostatic attraction or surface completion reactions. Sorption and precipitation are potentially reversible, so removal of reactive medium and gathered products may be necessary for continued remediation. The second one is transformation. Transformation involves taking the contaminant and transforming it to a less harmful or non-toxic form. The main benefits of transformation is that it does not necessarily require removal of the reactive medium, unless the reactive medium must be replaced due to decreased effectiveness or clogging. Transformation most commonly takes the form of an irreversible redox reaction. The medium may directly supply electrons or for reduction or stimulate microorganisms to facilitate electron transfer. In some cases, remediation of contaminated groundwater can be achieved by both processes that take place simultaneously. Moving to the next slide. Types of reactive material. PRBs use specific reactive materials to facilitate the treatment of contaminants as groundwater flows through them. The choice of reactive material depends on the types of contaminants present at the site. Here are some common reactive materials employed in PRBs. First one is zero valent iron or Fe0. Second one is activated carbon. Third one is calcium carbonate, also known as calcite. Fourth one is organic substrates. Fifth is hydrogen producing materials. Sixth one is permeable reactive iron minerals like apatite. Seventh one is sulfate reducing materials. Moving to the next slide. Types of reactive materials and geochemical processes used for the different types of contaminants. First reactive material is zero valent iron or Fe0. It is used for contaminants like chlorinated solvents and heavy metals by geochemical process adsorption. In adsorption, basically the contaminants stick on the surface of the reactive materials. Second one is granular active carbon. Granular active carbon is used for contaminants like volatile organic compound and pesticides by process adsorption. Third one is amorphous ferric oxyhydroxide. It is used for contaminants for heavy metals like arsenic and lead by sorption process. When adsorption and absorption take place simultaneously, it is termed as sorption. Fourth one is BOFS, basic oxygen furnace slag. It is used for contaminants like heavy metals by process reduction and precipitation. Fifth one is ion exchange resins. It is used for contaminants like heavy metals, certain cations by process precipitation. Sixth one is limestone. It is used to remove acidity and certain heavy metals by precipitation process. Seventh one is apatite. Apatite used for phosphate compounds and some heavy metals by reduction and precipitation process. Eighth one is sodium dithionite. Sodium dithionite is used for chlorinated solvents and certain heavy metals by microbial degradation. Ninth one is zeolites. Zeolites is used for ammoniums and heavy metals and some cations by adsorption process. 10th one is sand or gravel plus nutrients plus oxygen. It is typically used for promoting natural attenuation and biodegradation of organic contaminants. Promotes microbial degradation. Moving to the next slide. Applications of permeable reactive barriers. The main goal of PRB is to treat the contaminated groundwater. Here are some applications. First one is at industrial sites. PRB is applied at the industrial facility to treat groundwater contaminated with substances such as chlorinated solvents, heavy metals, and organic compounds. Second one is landfill and waste sites. At landfill and waste sites, PRB is used to treat the migration of contaminants such as leachate into the surrounding groundwater. Third one is mine sites. At mine site, PRBs are implemented to treat the groundwater contaminated with metals and other mining related pollutants. Fifth one is military installations. At some military sites, to address the groundwater contamination resulting from the historical activities like war, where contaminants are fuels and solvents. Sixth one is nuclear facilities. At nuclear facilities, PRBs may be used to manage and remediate groundwater contaminated with radioactive substances. Sixth one is brown to green field conversion. PRBs can facilitate the conversion of brownfield sites to greenfield by remediating the contaminated subsurface and ensuring environmental sustainability. Seventh one is urban and residential areas. In urban and residential areas where historical industrial activities may have led to groundwater contamination, PRBs are installed to protect the drinking water resources. To the next slide. Benefits of permeable reactive barriers. First one is cost effective. Compared to other remediation methods like pump and treat method, PRBs are generally less expensive to install and operate. They require minimal infrastructure and no ongoing energy input for operation. Second one is long lasting. PRBs can function effectively for many years, sometimes even decades, with minimal maintenance. The reactive materials can be designed to have slow release rates, extending their lifespan. Third one is minimal disruption. Installation typically causes minimal disruption to the surrounding environment and existing infrastructure. There is no need of extensive excavation or removal of contaminated soil. Fourth one is passive treatment. PRBs operate passively, meaning they don't require pumps, membranes, or other active equipment. This eliminates the need of ongoing energy consumption and reduces the risk of operational breakdowns. Fifth one is versatile. PRBs can be used to treat a wide range of contaminants including organic solvent, metal, arsenic and chlorinated compounds. Moving to the next slide. Limitations or challenges in PRBs. First one is site specific. PRBs need to be carefully designed and installed to suit the specific site conditions and contaminant types. Factors like groundwater flow rate, aquifer chemistry, and contaminant characteristics must be considered for optimal performance. Second one is monitoring required. Regular monitoring is necessary to track the performance of the PRB and ensure its functioning effectively. This may involve groundwater sampling, analyzing the reactive media, and track the plume movement. Third one is not suitable for all contaminants. Not all contaminants are treatable using PRBs. Some highly mobile or recalcitrant contaminants may bypass the barrier or not be effectively immobilized by the reactive media. Fourth one is potential for clogging. The permeable material and reactive media can become clogged over time by sediment or precipitation products. It results in the reducing of flow rate and effectiveness of PRBs. Fifth one is limited radius of influence. PRBs primarily impact the groundwater flowing directly through them. They may not be effective for treating contaminated areas outside their immediate vicinity. Moving to the next slide, case studies. The first case study from East Helena, Montana. Types of contaminants are arsenic, selenium, lead, cadmium, and zinc. The type of wall used by configuration is continuous trench. Dimension is 9.1 cross 13.7 cross 1.8 to 2.4 meter. Type of reactive material used is zero valent iron. After installation of PRBs and monitoring for 2 years, it is found that the initial arsenic concentration was more than 25 mg per liter, and after 2 years it becomes 2 to 1 mg per liter. It means 99% removal of arsenic from groundwater. There is no change in the hydraulic conductivity of the PRB that would indicate the corrosion and a precipitation buildup. The second case study from near a riverbank, Campania, Italy. Type of contaminants was cadmium second. Type of wall used is continuous trench, and reactive material is used GAC, granular active carbon. You can see in the image PRB completely remediated the cadmium from the groundwater for the first 3 months. After that, barrier began to saturate but sustained an overflow concentration of cadmium below 0.005 mg per liter for over 7 months. The simulation results also showed a peak concentration of cadmium at the center of the PRB was due to the desorption and resorption of cadmium when clean groundwater flowed through. Moving to the next slide, future of PRBs. Use of nano-enhanced material could lead to PRBs that tackle a wider range of pollutants, including emerging contaminants like pharmaceutical and microplastics. PRBs embedded with smart materials that sense depletion and trigger targeted regeneration process, like a phoenix rising from the ashes of contamination. PRBs could be configured as 3D curtains or targeted zones, providing more nuanced control and adaptability to complex contamination plumes. PRB is equipped with sensors that continuously monitor contaminant level and adjust their reactivity or flow dynamics in real time for optimizing performance and minimizing energy consumption. Moving to the next slide, conclusion. PRBs offer a valuable and powerful tool for tackling groundwater contamination. PRBs advantages and including cost effectiveness, longevity, minimal site disruption and passive operations make them a compelling choice for a variety of remediation projects. PRBs offer a sustainable and practical approach to groundwater remediation, but their successful implementation requires thorough site assessment, appropriate design and ongoing monitoring. Hope I was able to provide a brief information about permeable reactive barrier technology. If you have any thoughts or questions, please let us know. Thank you. Have a great day.